And so we're going to start tonight's session with the first keynote lecture by Yuh Nung Jan. And I kind of implied that rarely we have even a talk on ion channels, and that seems to imply that I would have a lot to say when really do a talk and do some special introduction. So I went back to my file of one of the early introduction I did, and I thought it's still very relevant until today, which is when I first joined Lee's lab as a postdoc. The story I heard was that the shaker is cold and punctuous, potassium and boost tempo. They're about to leave, and Lee told them, you three discuss and decide what you want to do and tell me what's left. So the postdoc discussed and then decided what they want to do. And I'm not exactly sure what they told Lee was left. But in the last 20 years, it appears that there are a lot left to me. So today we are very honored to have really give a keynote on both potassium channel and calcium-gated chloride channel.
Thanks very much, and having a really good time. All the organizers. It's a wonderful meeting. For the ion channel studies, that's part of long-term collaboration at Keynote. We've chosen the approach to start, if we can, with molecular identification. So then we can study the channel one at a time. What I will do is to tell you some of the recent studies. There was a surprise that linked to a potassium channel regulation to daylight toxicity. So I'll tell you that first, and then tell you about some other surprises we ran into for this new family of ions. So for the voltage-gated channels, as we all know, several members of this large family are linked to different diseases of the brain, the muscle, the heart, and so on. And also for the channel regulation like immunoactivity, we've seen multiple times that it involves signaling molecules in the pathway that's linked to disease, like tuberous I'm always stumbling with that one. Yes, tuberous sclerosis complex. There we go. So it's a negative regulator of mTOR. So when Shibin Yan started his postdoc, he was looking at the mTOR signaling, initially thinking about regulation of voltage-gated potassium channel. But quite by chance, he came to a different story that mTOR, a particular type of central neurons, regulate KATP. And as we know, KATP is a channel that's sensitive to metabolic regulation, KATP sensitive. And in the periphery, it controls insulin release from pancreas. And that's why loss of function mutation will cause hypoglycemia, while gain-of-function mutations are linked to neonatal diabetes. But what happened was Shibin being frugal actually included some really old mice in his study, and then noticed that the signaling is quite different. So in these neurons that express POMC, the precursor, the peptide precursor for alpha MSH, in the old mice, there's a quite high level of mTOR signaling, and this is the phosphorylated form of M6. And since the alpha MSH is released in multiple brain regions, including this one, the PDN, and the function of this peptide is to regulate appetite and other forms of homeostasis or to control body weight. And so that kind of made Shibin think of the real-life toxicity. when he reported from these neurons, from old and young mice, there's a difference in the input resistance. The old mice have lower input resistance, more hyperpolarized membrane potential, and they are just not firing as robust as the same neuron in the young mice. And so that kind of smells like some potassium channel is just too active in these neurons. And when being applied the transmitter receptor inhibitor antagonists, that didn't change the general feature that the neurons are firing repetitively for the POMC neurons from the young mice and not from the old mice. But blocking KATP channel with glibenclamide allow these neurons to fire repetitively again. So that indicates that there is increased KATP channel activity in the POMC neurons from old mice. And indeed, he could see the current, the full-blown current, if he removes the ATP entering the K channel opening. So this channel is in the KIR family. The alpha subunit is KIR6.2. The beta subunit is the sulfonylurea receptor, SR1. With single cell RT-PCR, Shibin could see a pretty robust upregulation of KIR6.2 message in the POMC neuron when the neurons are from the old mice compared to the young mice. So then the next question is what might be the connection between these two phenomena. In the old neurons, there's elevated mTOR activity, there's elevated KATP channel activity, and actually expressed from KIR6.2. To test whether there is a causal link, use the conditional knockout mice to remove the negative regulator of mTOR only in POMC neurons. And that caused hyperpolarization. But he did the same thing, removing TFC1 from the AGRP/MPY neurons. There's no effect on the resting potential or the firing pattern. And that's most likely because the mTOR activity is already very high in these MPY neurons in the young mice. But in the old mice, there's causing an increase in mTOR activity, caused an increase in KATP and a reduction of firing, and also a reduction in the release of alpha-NSF into the end. And so that also has some effect on the body weight. Indeed, these mice are growing quite a bit in weight. And this is only 3 months old. And so, so if we see that the mTOR activity is directly linked to the neuronal activity and the body weight, then the next question is, can we reverse the whole process in the old mice if we just provide the inhibitor for mTOR, rapamycin? So to avoid complication of side effects from the action of in the periphery, should we basically put a little backpack on the old mice and introduce the rapamycin directly to the brain, to the ventricle, and that indeed reverse everything. So if it's only the vertical control, we see that the neurons are silent in the old mice. And if we block the ATP channel, then they start firing. And with rapamycin infusion, the neurons are firing a lot. They have reduced, the ATP current is not so high anymore, and the membrane potential is not so hyperpolarized anymore. And there was also a reduction in the projection of POMC neuron to the PDN. That's also restored with the rapamycin infusion. So to summarize then, so here's the body weight. So that's the important part. rapamycin infusion indeed caused a loss of body weight in the old mice, and also kind of a reduction in appetite in the food intake. So it kind of it was a relief, right? It's not our fault when we get it's getting hard to control body weight. There's a basis that the mTOR signaling is increased with aging in the POMC neuron. And that causes an upregulation of KATP channels to silence these neurons to reduce the release of alpha and NSH. And everything can be reverted from this stage to this one by just inhibiting mTOR in the old mice. So as we are doing these studies on the potassium channels, we are also aware that even in this day and age, there are still orphan receptors with unknown or unsettled molecular identity. And one example is the calcium-activated chloride channel, as you can see from this lamenting title of a review not so long ago. So CACC is actually a well-known channel. It's expressed in many different cell types. It's known from studies in the 80s. It's also expressed in the green algae, an organism that predates the land compass. Before there's anything stirring on land, the green algae was around way back when. And these organisms don't have voltage-gated sodium channels, but they fire action potentials to control protoplast streaming in these really large cells, and they rely on CSHL to generate action potential. So for the intrinsic biological interest of these channels, and also for the potential of this channel as a drug target, there's been quite a bit of effort. But the reason it's so difficult, partly is because the channel is so widely expressed. It is expressed in the xenopus oocyte for the purpose of preventing polyspermia, which means we cannot use this as the expression system, or expression protein. And so what Bjorn Schroeder resorted to was to look at other amphibia like the salamanders. Some are physiologically polyspermic. And he found out that the axolotl oocytes don't have much endogenous CACC. So he used these oocytes as the expression system, and the xenopus oocyte as the donor for the message. And the expression cloning led him to TMEM16A as the calcium-activated chloride channel from xenopus. It took a while. It took another 6 years for this project. But finally, when we got to this point, two groups, one from Korea and one from Italy, taking completely different strategies, independently came to the same conclusion that TMEM16A is the CACC. We also tested TMEM16B and found that that also forms CACC. And by now, we have seen multiple studies in the literature that 16B corresponds to the CACC in the olfactory neuron cilia, where it's been proposed for a long time by physiologists that it provides the function of amplification. It's a high gain, low noise amplification of the odorant response. And it's also in the nerve terminal of the photoreceptors in the retina, where it probably provides negative feedback on the calcium. And now, looking at the central neurons, we know from many studies summarizing this review that for action potential firing, there's calcium channel activation, and the calcium entry will activate calcium-activated potassium channels on big conductance methane. And for the synaptic potential generated by glutamate receptors, NMDA receptors will allow calcium entry, and that will activate calcium-activated calcium channels of small conductance, SK. And so then when Wendy Huang was choosing thesis project, she wondered whether there's also calcium-activated chloride channels in these hippocampal neurons, and what these channels might do to the neuronal signaling. So she worked together with two postdocs, Xiaohua and Fan, first to see that it's actually 16B rather than 16A RNA present in the hippocampal neurons. This is in situ to see the expression in both excitatory neurons and interneurons, actually. And with antibodies, we can see the protein production in these hippocampal neurons. Wendy developed first just a test with calcium channel activation. The calcium current is followed with a tail current. And by looking at the reversal potential at different chloride concentration and so on, she concluded that this is CACC. It's blocked by CACC blockers, and it's also reduced by two different shRNA to knock out 16B. These shRNA also cause a broadening of action potential, and again, the channel blockers will do the same. And what we see is that for CACC, it controls the action potential width in the somatodendritic region, but it doesn't seem to affect the action potential duration in the terminal. So in that aspect, it's different from FDK channels. And the reason we believe this is the case is the synaptic response mediated by anti-receptor is not altered when we apply the blockers for CACC. But if now she looks at the postsynaptic side, when the response gets big enough, it will activate NMDA receptors to allow calcium to come in, and that will activate CACC. Because when she applies the blocker for CACC, there's an increase in the EBSP, the postsynaptic chemical. And this modulation depends on the chloride concentration. So with physiological low chloride, we see that the CACC function is to reduce the EBSP size. But if she raises the internal chloride, then the CACC function is the opposite as we imagined. And when she had a calcium chelator in the peptide, so for every experiment she did everything three times to make the point that the blocker is really acting on the calcium-activated chloride channel. And so we see that with a low chloride, the function of this channel is to reduce the excitability. This is a trend of EBSP, and also to reduce the action potential duration. But the effect will be turned into its head will be opposite when the chloride concentration is high. It's actually relevant to consider this scenario because the chloride homeostasis varies with action potential firing. For example, Wu Mingfu had a paper just by increasing the firing frequency. This could change because of the regulation of PCC2. And also in diseases, epilepsy, brain trauma, there's an increase in internal chloride. So there's always the possibility that when that happens, then these channels, instead of being neuroprotective, could be exaggerating the problem. So to summarize Wendy's thesis study, we find that there is CACC in hippocampal pyramidal neurons. It's dependent on 16B. It controls the action potential duration in the somatodendritic region, another nerve terminal. It dampens the synaptic potential in the postsynaptic side. It also reduces EBSP to spike coupling by increasing the threshold for firing action potential. And in both cases, so in this case, CACC must be just nanometers from the calcium channels to control the active potential duration. At the postsynaptic side, CACC must be only nanometers away from NMDA receptor, because in both cases, the fast calcium chelator backpack will abolish the CACC activation, and not the slow chelator, BPK. And that, by the way, also applies to BK channel in the somatodendritic region and the SK channel in the postsynaptic side. And so we see that these three types of calcium-activated ion channels have three distinct patterns of regulating neuronal activity in these circuits. What might be unique for the CACC is both the chloride concentration and the calcium concentration will vary with neuronal activity. I didn't tell you much about 16A, but it's also a calcium-activated chloride channel. It's present in the secretory cells, in the exocrine glands, airways, and so on. So it was quite a surprise when Huang He expressed 16F in the axolotl oocytes. It turned out it's not a CACC. So the channel is activated by calcium and by voltage. And recently there's a paper from Chris Hartzell identifying one glutamate residue in 16A that's critical for calcium activation, because replacing the glutamate with alanine or glutamine in this case will reduce calcium sensitivity. And making the equivalent mutation in 16F also greatly reduce the calcium sensitivity. So it's quite possible 16A channel and 16F channel use similar mechanisms for calcium activation. But in the experiments, if we just keep the internal calcium level high and vary the concentration of sodium chloride, we see that the reversal potential for 16F is going in the opposite direction compared to 16A. And so that indicates that the 16F channel is allowing sodium to go through rather than chloride. And indeed, when Huang He replaced chloride with very large anion, the 16F channel still permeates the sodium. And the sodium to chloride permeability ratio is about 7 for 16F. For 16A, it's the opposite. Chloride to sodium permeability ratio is about 7. And when we look for the sequence that's different between the chloride channel, 16A and B, and the cation channel that permeates sodium, 16F, there's this one position that's lysine for the chloride channel, but glutamine for the cation channel. And when glutamine is replaced with lysine in 16F, the channel kinetics is altered, but more importantly, the cation selectivity is reduced. And conversely, in the 16A, if the lysine is replaced with glutamine, the anion selectivity is reduced. Now, the 16F channel permeates not only sodium, but also potassium. When we have the solution set up that there's only potassium as the cation. So that kind of raised the question, is 16F10 a calcium-activated, non-selective cation? Not exactly, because the 16F channel also allows really large cations, TA, NMDG, up to about 7 angstrom radius with monovalent cations to go through. It also allows calcium to go through. So in this case, the only cation is calcium, and when the patch is excised, the channel is active, it's passing calcium ion. So this is quite different from the 10 channels that are not so permeable to that latent cations. And another thing that's different is for the CAN channels, remember, those of us who have been in the field for a while will remember, when the patch clamp technique was just developed, and as soon as people excised patch, they reported the CAN channels. You excise patch inside out, you raise calcium, and there you go, you have the single channel activity. And the single channel conductance is separate between 20-30 ppc. But for the 16F channel, it's really tiny, so it was a struggle to deduce the single channel conductance based on noise analysis. And so, kind of by analogy to SK channel, we call it SCAN because it's a small conductance. Calcium activated, non-selective cation. And since it's a calcium activated channel that allows calcium to go through very well, it may be necessary for these channels to have really small conductance. Kind of similar scenario as the crack and the sock. If the channel can have a positive feedback, the calcium activation will allow more calcium to come in. To have it just let a lot of calcium to come in may not be such a good thing to the cell. So that was, we thought, enough surprise for us, but at this point we came upon more surprise. Just around that time, a paper came out linking TNEN16F to the Scott syndrome. It actually pointed out that Miss Scott, for whom this eating disorder is named, Scott syndrome, has a mutation there. So she doesn't have TNEN16F. And the problem with the Scott syndrome is there's a deficit in the calcium-activated scramblings. So that takes us to the lipid bilayer asymmetry. The different phospholipids, some are more prominent at higher level on the outer leaflet, and others like phosphatidylserine is only on the inner leaflet normally. And this asymmetry is set up by the flipises and flopises. These are the real names. So these are the proteins that require energy to bring lipid from the outer leaflet to the inner leaflet, or the inner leaflet to the outer leaflet. But then when we get a cut and the platelets get activated, the calcium level goes up inside in the intracellular cytosol of platelets. That activates the scramblings that just scrambles the lipid from the inner and outer leaflet. And the end result is phosphatidylserine is exposed to the cell surface. And that serves as the anchor for all these tissue factors, the CAN, A5. And in the end, it leads to the production of thrombin, the cleavage of prothrombin, to generate thrombin, and that leads to blood coagulation. And so it was actually amazing that all this linkage was possible because Ms. Scott is out to be more than 100 years old now, and her parents obviously older. But the researchers who studied these patients get immortalized the B-cell lines. So for these diseases, it's really their blood cells and the few cell lines that were available. So what Andrew Kim, a postdoc in the lab, did was to generate the knockout mice and see if we can now have a mouse model. These knockout mice without 16F have normal blood counts, but their platelets and other blood, basically all the cells don't have 16F. And when the platelets are activated artificially with the calcium ionophore, with 16F, we see the